Welcome to my e-lecture. I am Rune Martin Holt. I'm professor at NTNU in Trondheim, Norway, within the Geoscience and Petroleum Department. The title of my presentation is The Importance of Overburden Stress Path in Assessment of Stress Dependence for 4D Applications. I'd like to acknowledge my co-authors, Andreas Bauer, who is an adjunct professor at NTNU and works at SINTEF, and Audun Bach, who also works at SINTEF in Trondheim. The outline is as follows. I will start by introducing you to the overburden stress path and then discuss about stress path dependence of wave velocities. I will show you experiments, results of laboratory experiments with shale cores. I will explain what impact these results have on the commonly used dilation factor, the so-called R factor in 4D seismic analysis and interpretation. And I will end up by showing you some possible consequences for 4D interpretation. So this slide is introducing the overburden stress path. In the picture you see a reservoir in the middle. In this case, it's depleting, so the pore pressure is reducing. When the pore pressure is reducing, the reservoir is compacting. That leads to a stretch in the overburden and hence a vertical stress reduction above the center of the reservoir. However, this is compensated by an increase in the horizontal stress right above the center of the reservoir. At the edges of the reservoir, the situation is opposite. The vertical stress is leaning on the shoulders of the reservoir and is increasing there, whereas the horizontal stress is reducing. All this is driven by pore pressure changes in the reservoir. I said depletion, but it could also be inflation caused by injection of, say, CO2 in a subsurface reservoir. It's evidence in 4D seismic that we have these stress changes. That is seen by slowdown of seismic waves above depleting zones, like was pointed out by Hatchell and Bourne in 2005. And it's also seen as a shear wave splitting above the rim of the depleting zone, as was shown by Barkved and Christiansen in 2005. So how is the overburden stress path? Theoretically, we base the overburden stress path often on the work by Gertsma in 1973. Gertsma assumed linear elasticity, isotropic rock, no poroelastic effect, and that the subsurface is perfectly homogeneous. That means no elastic contrast between the reservoir and its surroundings. This has a remarkable consequence, namely that the mean stress is constant everywhere outside the reservoir. This is illustrated by the green color in the insert to the right in the middle of the slide. The graph in the middle of the slide is showing the stress path coefficients. The stress path coefficients are defined as follows. Gamma V is a vertical stress path coefficient that relates the change in the total vertical stress to the change in the pore pressure in the reservoir. And the gamma H likewise represents the change in the horizontal stress with respect to change in the pore pressure in the reservoir. The reservoir in the graph is a little gray line in the middle there, and you see the vertical gamma as the fully drawn curve and the horizontal gamma as a dashed curve. The vertical gamma is positive everywhere. Since depletion implies a negative pressure change, it means that the vertical stress is decreasing above the center of the reservoir, whereas the horizontal stress is increasing. And you see that the ratio, or you may see that the ratio is 2:1, so we have constant mean stress. The other interesting feature about this graph is, well, there are two interesting features. One is that the stress path coefficient varies with depth. The other is that the stress path coefficient changes dramatically over a very large range of depths from about 2,000 to 3,000 meters. So about 1,000 meters of rock is involved in the stress change caused by the depleting reservoir. And this is one of the reasons that we can pick up 4D effects from the reservoir. Large volumes of the overburden are affected. The stress path is governed by the aspect ratio, which is the height over diameter of the depleting zone, and the rock parameter that most influences on it is the Poisson's ratio. Stress arching, as described in the previous part of the presentation, will increase if the overburden is stiffer than the reservoir. In order to do this analysis, we have to use numerical models. For this purpose, we used finite element simulations, and the simulations were done with a reservoir at 3000 meters depth, with an aspect ratio or thickness to diameter ratio of 0.1, and with Poisson's ratio equal to 0.3 everywhere, also outside the reservoir. What we found then was, and we can see that from the graph at the bottom, that the vertical stress path coefficient, which are the solid curves, the blue one is for a horizontal reservoir, increases with increasing elastic contrast, so that arching increases with increasing elastic contrast. And we also see that the dashed curve, the horizontal gamma, increases with increasing stiffness contrast. In fact, the horizontal gamma becomes positive for about a ratio of 2 between the Young's modulus of the surroundings and the Young's modulus of the reservoir. That means that both horizontal and vertical stress would decrease in such a case, and if that happens, it can have some impact on the ability to drill stable boreholes through the overburden. The red curves for the gammas show what happens if we have a tilted reservoir, and we see that arching is promoted by reservoir tilt. In addition, non-elasticity, plasticity or faulting will affect the stress path further, but we do not address that directly in this presentation. Now we look at the stress path dependence of velocities, and the main assumptions we will make is that the velocities depend linearly on stress or changes in stress. If you look at the curves in the figure to the right in the bottom, they are from David Johnson's geophysics paper in 1987, where he showed results of loading, unloading, isotropical stress path of Kimmeridge shale. And it was done at 2 different temperatures, but the main point here is that the behavior over large ranges of stress is almost linear. In the lower right corner, you see some results from a constant volume test, which is pretty close to a constant mean stress test that we did with another shale a few years ago. And we see that the vertical and the horizontal P-wave velocities, both of them show relatively clear linear trends as a function of stress for the stress changes that we applied. So this makes it feasible to write an equation that relates the velocity change or relative change in velocity to changes in the stress in a linear format. We chose to write that as the velocity change as a function of the change in the mean stress with a proportionality coefficient that we call A, and the change in the shear stress with a proportionality constant that we name B. And furthermore, we also assume that there is a linearity in the velocity with change in pore pressure with a proportionality constant C. The subscript J denotes that this could be any P wave or S wave along any direction in the material. Then we define a stress path, and for the laboratory experiments that I will show you next, the appropriate definition of the stress path is that it is a change in the radial stress, delta sigma r, divided by the change in the axial stress, delta sigma c. This implies, since the pore pressure change is also expected to exhibit linearity, according to Skempton's equation from 1954, shown at the right in the bottom, this implies that the velocity change will be linear in the stress path coefficient kappa. So when we do different stress paths, we should expect linearity. So I will now turn your attention to some laboratory experiments that we did. They were done in a triaxial setup with controlled and monitored axial and confining pressures. Axial strains and the radial strains were measured, and the pore pressure response was recorded. Multidirectional P and S wave velocity measurements were performed with ultrasonic frequencies around 1 megahertz or lower, permitting determination of the full transversely isotropic elastic anisotropy. The materials used were different kinds of shales, mostly field shales, and I will show you data here for one of them, which is a well-preserved high porosity, 25% porosity, and high clay content, 76%, presumably fully saturated shale, which is typical of overburden shales from our part of the world. Here's how we do the tests. Normally, people do laboratory experiments where they measure wave velocities along one stress path only, and that is usually the hydrostatic or isotropic stress path. But here we applied 4 different stress paths. They were all undrained. That means that no pore fluid can escape, and the pore pressure can change within the samples as we are testing them. If you look at the figure, you see the different cycles of stress path that we did. The ISO means the incrementally isotropic stress path. But before we did that, we had to load the sample to its in situ conditions. So I have the in situ vertical stress there, around 50 megapascal. We have the in situ horizontal stress, 47, 48 megapascal. And the pore pressure in blue, 34, 35 megapascal. And probably you notice that it took a long time to get to that point where we actually start the test that I will show you the results of. It took 175 hours. So this is a quite time-consuming test because of the very low permeability of this shale. Then the 4 stress cycles, they were the isostatic, as I said. That means that the kappa is equal to 1. The triax is uniaxial stress, so no change in the radial stress, as you see from the red curve there. So kappa is 0. K0, which is uniaxial strain, and at the end, the constant mean stress, or CMS, where kappa is equal to -1/2. In all these segments, the pore pressure was recorded, and you can see the pore pressure recording at the bottom of the graph. So this slide shows the most important result of this presentation. It shows the stress sensitivity of the vertical P wave velocity as a function of stress path. And as you see, the 4 points are approximately well confined to a straight line, so I think we can agree that the linearity of stress path sensitivity was confirmed for this field shale core. The influence of stress path is significant. The change when you go from the constant mean stress to the left to the isostatic stress path to the right is a factor of 2 or slightly more than that. This shows only the axial P wave. I could have showed you S waves or horizontal P waves, but they all show very similar linear trends. This is measured pore pressure response. Remember, we referred to Skempton. Skempton in 1954 suggested, on an empirical basis, a stress path dependence of the pore pressure change in undrained experiments. Described by 2 parameters, the Skempton B, that describes the behavior of the isostatic test when kappa is equal to 1, and AS, the Skempton A, that describes the influence of the deviatoric or the shear stress. Our data points fall perfectly on a straight line and confirms Skempton's relationship. This means that from the experiments that I showed you, we determine the Skempton parameters plus the A, B, and the C parameters. That means we have everything we need to calculate velocity changes along any stress path. Let me dwell a few moments with the dilation factor, or the R parameter, that is quite popular in use in 4D seismic interpretation. It stems from work of Röste and co-workers and by Haschel and Born, presented in 2004 at an EAGE conference, and is a measure of the strain sensitivity. The R factor is the relative velocity change divided by the strain. But the strain is a static quantity that depends on the stress path, and we have that from Hooke's law. So if we shift around a little bit the terms of the R factor, we find that it is the stress sensitivity. You see that in the left-right corner on this slide. The relative velocity change with respect to stress, that's the stress sensitivity, multiplied by a stiffness. And the stiffness is a function of the stress path that follows directly from Hooke's law. The graph that you see draws the R factor as a function of stress path, provided that the stress dependence is constant. That means it does not depend on stress path at all. And we see that still the R factor increases strongly with stress path. And the reason for that is simply that the axial strain becomes smaller with isotropic stress than it is with any of the other stress paths, and that is a direct consequence of Hooke's law. In the equation below the figure, you see that if Poisson's ratio would be 0.4, kind of, which is not untypical for soft shales in the overburden, and kappa would be equal 1, which is the isotropic stress path, the stiffness parameter, delta sigma over delta epsilon, can be very large. And that is why R is growing so much with stress path. Here you see the data for the field shale. The R factor is increasing from about 2 for the constant mean stress to a value between 15 and 20 for isostatic loading. Mainly because the axial strain is reduced. In this case, the R is calculated from the measured velocity changes and measured axial strains. So, what are the consequences of this work for 4D seismic? We can estimate the change in travel time that we record during 4D in situ versus reservoir pore pressure change by using the laboratory measurement of stress path dependent sensitivity of the velocities. That's the A, B, and the C parameters. The laboratory measured Skempton parameters, AS and BS, from the pore pressure measurements, and then the in situ stress paths coefficients, gamma V and gamma H, that we get from the geomechanical modeling. Now the kappa, representative of in situ condition, is simply the ratio between the gamma H and the gamma V. And since we calculated that earlier in the presentation as a function of elastic contrast, we can calculate the relative velocity change with change in the reservoir pore pressure, and that's shown in the graph that you see here. The blue curve represents the flat reservoir. The red curve represents the tilted reservoir, and you see that there is a large increase in velocity stress dependence, or velocity pore pressure dependence, I should say, with increasing elastic contrast. So let's wrap up what the main consequences for 4D interpretation are. The in situ dilation parameter, the R factor, can be estimated, but that requires additional knowledge of static elastic moduli. On the other hand, if we obtain R as a function of depth, we may use it to assess the in situ stress path from 4D data. One thing we should notice is the sensitivity of the 4D response to pore pressure changes in the overburden. We saw that through the influence of the Skempton parameters. It's quite often assumed that nothing happens with the pore pressure in the overburden because of the very low permeability of the shale. On the other hand, the very low permeability of the shale means that there is no chance for fluid to flow, at least not instantaneously, into the shale or out of the shale, and that means that the behavior is undrained, and undrained behavior implies pore pressure changes. And these pore pressure changes may have important operational aspects, for instance, with respect to drilling. Notice that the stress and the stress path sensitivities may be different from what we have seen here, measured at ultrasonic frequencies, if we measure at seismic frequencies. Such laboratory measurements are underway in our laboratory, and we can see differences, but we do not yet have the complete picture. However, measurements are needed, and a reliable dispersion model is also needed. So conclusions then. Linear stress sensitivity implies linear stress path sensitivity. Ultrasonic measurements confirm the validity of the linear stress path dependence in shales, in particular when tested near their in situ stress state. And geomechanical modeling can translate the laboratory measured stress path sensitivity into expected velocity changes in the field. Finally, let me acknowledge the financial support that we had from the Research Council of Norway and a number of industry partners, both for the KPN project Shale Rock Physics and for the ROSE program at NTNU. Thank you for your attention. If you liked this presentation, you can share it, and I'm sure you would like to see if there is any other interesting e-lectures out there at the EAGE YouTube channel. Thank you for your attention.